SensorEra provides proprietary ground motion sensing solutions that span across multiple industries from energy and seismological through to mining and geotechnical applications. Our self-powered autonomous devices are low cost, high precision, and leverage the latest technology of the Internet of Things. Whether the ground motion is naturally occurring or induced by man-made activities, our ultra-sensitive devices stream real-time ground motion alerts to you wherever you are. When combined with a seismic source, our 6-component devices provide unique information about the deep and shallow subsurface below our feet. Such information is critical for geostorage applications such as carbon capture and storage, or CCS. SensorEra provides complementary autonomous permanent seismic sources. When combined with our sensing technology, a powerful tool is created for initial site characterization and continuous site monitoring of deep fluid and gas motion, such as that found with CCS Plume monitoring. Our real-time cloud-based processing flows send actionable results to our map-based web portal on your handheld device or laptop, wherever you happen to be in the world. Each Seismicity alert module is made up of the sensor device, powered by a battery, which is charged by a solar panel. An antenna is also included that contains GPS, 4G, and Wi-Fi transmitters. The footprint is very small. You can see from the photo in the middle that the mast is supporting, in this case, a high gain 4G antenna in places where the cell phone signal is weak, plus the omnidirectional antenna on top, which contains the 4G and GPS. The battery is buried, as is the 6-component motion sensor, in this case buried down to 3 feet. So each sensor measures all 6 degrees of freedom. In addition, a 3C magnetometer measures the orientation of the tool when it is installed into the ground. Each sensor pod is hermetically sealed to last for decades in harsh environments. It's compact in size and lightweight. This means it is a very fast field deployment, approximately 30 minutes per station, depending on ground conditions. In addition, it's sometimes necessary to erect a cattle fence around each station, which can increase the amount of time per station. The sensors were designed to be installed permanently, but can equally be installed in temporary situations, such as for frac monitoring. They contain a very small surface footprint, and we would expect to only need to visit each site every 3 to 4 years to change the battery. The firmware and other interrogation of the unit itself can all be done remotely. We use 4G and Wi-Fi communications. In addition, it is possible to hook the device through satellite communications through the Starlink system. Each recorded sample is GPS timestamped, and each station is kept at a very low cost. We can include, optionally, for security purposes, 24/7 webcam observations, and in our next generation we will be providing RTK GPS-based subsidence monitors. Our sensors measure 3 rotational velocity channels in addition to the translational acceleration. With a hammer source and a line of receivers above a buried, empty and water-filled container, we were able to directly extract the wave propagation velocity below each sensor. The velocity profile shown identifies both containers. This method is useful for shallow velocity profiling of weathering layer changes and even for buried hazard identification. Other benefits include high precision back azimuth estimates between the source and receiver, as well as real-time moment tensor inversion. Numerous comparisons and tests are now complete with our new era of ground motion sensors contrasted with pre-existing and expensive seismometer equipment. Our low-noise MEMS-based sensing device has been shown to perform as well as or outperform the legacy equipment. Here we show a long-range intercontinental earthquake as recorded by our station that is co-located with a traditional seismometer. The red and the blue traces show the seismometer 3C translational response, whilst the black traces show the SensorEra data for the same earthquake. We see the same consistency at all ranges and down to magnitude 0 for proximal events. The microvib, autonomous vibrating source, is provided through a partnership with GPUSA. The source consists of two offset masses that spin in opposite directions and at controlled and variable revolutions per minute. This allows us to perform various sweep designs, including linear and nonlinear upsweeps or custom sweep designs. When mounted on top of a helical pile, the resultant vibrating source is vertically aligned and compressional, much like a standard fiber-sized seismic source. Of course, this small unit does not have the hold-down force of a large surface fiber-sized truck, and instead is held solidly coupled to the earth by the helical fins at the base of the pile. Each pile is installed by a skid steer unit with at least 20,000 pounds of torque required. A SensorEra receiver is dropped to the base of the pile and used as a source monitor, and as a deep buried receiver when the source is not in use. The compressional wave energy is emitted from the base of the pile, so in most cases we are immune to the problematic shallow velocities and seasonal changes in the weathering layer. The source is easily moved between pile locations and is designed to operate for very long periods before any servicing is required. The source control unit is internet enabled, and the source can be controlled from any internet connection. In the new era of remotely operated solar-powered sparse seismic surveys, the microvib plus seismicity alert combination is unique in the marketplace.
At this private test site in California, we have installed 9 Seismicity alert stations that are continuously streaming ground motion information to our cloud server. All stations were installed in 2 days along 2 evenly spaced lines up to 3,000 feet in length. One line is roughly parallel to the west coast and the San Andreas fault system, the other is roughly tangential to the coastline. We analyze natural earth movements with our 6C sensors for continued geophysical software development. In addition, we run our remotely operated autonomous seismic sources at this site, and run daily seismic reflection tests from the comfort of our Houston office. It is here that we optimize helical pile depths and sweep parameters for short, medium and long offset source receiver pairs in preparation for CCS Plume monitoring surveys. SensorEra is the only company to provide low-cost 6C passive seismic monitoring that is optionally combined with autonomous and remotely operated seismic sources for a new completely solar-powered era of subsurface monitoring.